record it. All right, we're now recording. I pushed record. So in this case, you're going to get $8,000 a year, which I put up here. You should be able to see my nice Excel spreadsheet. Let me zoom in so it's as big as possible for you guys. Zoom selection. So they give you the interest rate 7%. How they came up with that, who knows? 30 years. Assume the guy's going to work for another 30 years, then he'll retire a millionaire. $8,000 per year. So because that's what they say. He's going to give him per year. So it's not an $8,000 once and then calculate. It sort of goes on forever. If someone made a mistake on the previous week's version of this, it's they try to discount this $8,000 over the entire period. No, it says per year. When it says per year, that means automatically you think the annuity. So they use the A for amount. In my day, we called it annuity, which by definition meant the same amount being paid year after year after year after year after year after year after year. Okay. So then it becomes a calculation issue of, I did it both ways on part A. So it says, what is the present value of this raise if interest rate is 7%? Well, you look at the back, present value of annuity on page 642, where 7% is, and you get this factor for 30 years, 12.409. Multiply that 12.409 times the 8,000, and you get this 99.27. Now, or you can use the present value formula, which I just used up here and said, okay, present value formula, highlight the interest rate, the period, the $8,000. Okay, and that gave me 99,272. Exact answer for both. Now for part B, it then asks you to go backwards. And this is the tricky part where it says, what's the future worth at year 30? Well, you still have an annuity because you're getting that period, 30 years. So your 30 years, 7% and $8,000 aren't changing. Or before you were saying, what's the present value of this? Now you're saying in the future, what will have been the value of getting that $8,000 for 30 years at 7%? Well, I go to that same page, 642, and get the F/A, where I think a future value of an annuity. We're here today, so we want the future value in 30 years. You look at that, and at the table next to n equals 30, and the FA column, you get 94.461. Multiply 94.461 times $8,000, get 75688. Or you can do the Excel version, future value, interest rate, time, amount of the annuity, and then you get 755,686. Again, the only difference between this future value and this for that $2 is rounding. The book stops at 3 significant digits. Excel goes on to like 9. That's the only reason you have a difference in a couple of dollars, and you should have been able to see that going on forever if you do it 2 different ways. I've showed you examples. If you're just a little bit off here and there between like the answer in the back of the book, answer in the back of the book tends, say tends because it depends, but as I've gone through it, I've done some comparisons. The older problems tend to be using tables. Newer problems tend to be using Excel. So there are certain problems I've watched where I say, okay, there might be similar problems. I do that manually for myself, and I think, oh, in order to get this number, he used the tables. In order to get this number, he had to use Excel. Well, problems that haven't changed in 10 years, use the tables. Problems that he just made up anew, probably by his, again, one of his doctoral students, have the Excel answer. So sometimes you have problems back the book, say, oh, I matched it perfectly last week. This week I didn't. It's most likely that the grad student who made the answer key used Excel in one version, and his predecessor, 5 years before, used the table version. Both are correct. And that's why I stress so much on your homework to show you the methodology you used so I can tell how you got what you got. All right, any questions on this before I go forward to 4.5? Hearing none, moving on. 4.5 was, oops, didn't have to change the page. Go back. How much must be invested now at 8% interest to produce $5,000 at the end of every year for 10 years? This is actually not an uncommon thing, and as we allude to in tonight's lecture, government works this way. You're thinking, okay, I want to be able to pull out $5,000 a year. And when you hear a lot of things about different trust funds and that out in the world, they know they're going to have certain expenditures every year. So you might endow something, and this is how professorships work. If you're very rich and want to have the Dr. Ian mathematics chair for the bestest professors ever, and you're going to have to pay someone a salary in that position, say of $50,000 a year. Well, if you want to know whether you can do that, you have to donate an amount. And if it's high enough to support that amount so you can pay the expenses of that professorship every year, they'll name a professorship after you, and you put this money in the bank, and the interest it earns every year is enough to generate the amount to cover the expenses, that $50,000 I said. So this time you're saying, okay, you got a professor, say you got a professor now who's really cheap. They work a part-time guy. You just have to pay him $5,000 a year. So how much do you have to invest so that every year you can pull out $5,000 without diminishing any of the investment for the rest of the time? That's what it's asking. So you have an interest rate up here. I did it in that should be a small n. There we go. Hit save so I don't remember why next time. Okay, the payment is the amount you want to pull out every year. Every year you pull out $5,000. That's why I made it negative. Again, if you made payment negative, present value positive, my purposes, I don't care as long as you're consistent. Present value is what you're putting in the bank today, which if was true to form, I'd highlight that in green. Boy, it must have been late night this night. Future value we don't care about because it's going on for 5 years, or 10 years it says. Okay, 8%, 10 years. Payment is what I want to have every year. So I did it by present value function. Say what's the present value of $5,000 a year every year for 10 years at 8%. I stick in the 10, the 8%, and the 5,000 in here. And that gives me the present value that in order to be able to draw out $5,000 a year for 10 years, I need to put in $33,550 today. So, or you can use the amount, and you're going to find that this week I stop doing things two ways in my demonstrations. I think by now you guess there are two ways. You can go to the present value of annuity on page 643, which has the 8% rates, and you go down to line 10 under the N, and that gives you 6.710. You multiply 6.710 times the $5,000 a year, and you get $33,550. Isn't that amazing? Any questions on that? Hearing none, I'll move on. Next we have 414. All right. A local finance company will loan $15,000 to a homeowner. It must be repaid in 36 monthly payments. Ooh, that gives you some compounding issues to worry about. Of $588 each. The first payment is due 30 days after the $15,000 is received. That 30 days, to confuse you, it's no different than saying our usual. We're always assuming the next cash flow comes 1 year later or one period later. So basically, at the end of period 1, you start getting the stuff in. It's due in 30. All right. So, interest rate they give you. Where is it? Oops, I've lost my place. Oh, look, 414. Finance companies pays. What interest rate are they going to charge you? So the interest rate is what you're looking for. So your present value is $15,000. How do you know that? Because they said you're going to get that today from the bank. Cool. Now then, what are you going to get to pay it back? Well, I put $15,000 positive because that's the money you're getting. From your standpoint, you're getting that money. It's positive. To pay it back, you're gonna have to pay back $588 a month. So you're paying that out. Cool. How many? 36 months. So what's the interest rate on that? Well, as I talked about last week, you have a function called rate. So you go in and you just, in the rate, you stick in the periods, the payment amount, and the present value. Or if you're dealing with a future value question, you put present value of 0 and future value of whatever it is. But it's asking you that because you want the rate it takes to make this present value go down to 0 in 36 months for this payment amount. The magic of Disney, it says 2%. Or you're looking at the, find the annuity given the present value. Okay, you get 0.3 that, and it gives you 6%. Now the problem with this one during the book version is that it's trial and error. I got this in here, well, how? Because I've done this problem many times and I knew it. But if you're going to use the tables to solve this, basically you've got to put out a guess and say, are you above and below? Basically put in these calculations and say, okay, apply a present value of an annuity, given that present value, and do the math on one. And if it's a little high, you go to the next interest rate lower, or the next page, and try it that one. Then it's too low. You basically go either side of it until you get close enough by trial and error to say, let's try this interest rate from the tables and this factor. Oh no, that didn't work. So then let's go higher, because it ended up with being too low for what I needed. Then you try it that one. If that's too high, then you go somewhere in between. But it's a trial and error period if you use the manual calculations. If you use Excel, you have a function called rate. Does anyone understand what I said about the trial and error part? Because that's the key on this, the really tricky part about this if you want to use that. Because we have different students in the class that some like using manual. We have a couple of people who love to do the detailed calculations. Most use Excel. Again, I encourage, don't require that. It's just, I encourage you to make it easy on yourself. But how many people are confused about what I said about this part right here, using the factors? Is anyone confused?
I don't understand. What is the rate formula doing?
Well, what it's doing essentially, and it's a summation series that converges. What it does is say, okay, if I want to pay back $15,000 at $508 a month for this time period, what interest rate makes that work? Because think about it, if you did it backwards, say you're going to have to say, you would do it backwards, say, I'm borrowing this, and you could also say, if I knew we negotiated 2%, if you want to know how much you're going to have to pay per month, you'd say, okay, $15,000 today, 36 months, and 2% interest, and solve for payment, it would give you $588. This is saying for some reason, maybe you just figured out you can afford $588 a month. That's what your cash flow says. All right, then what interest rate should you be charged if the bank says that's okay? That becomes the interest rate for this document that you're going to create, this loan. Again, if you do,
Okay.
let's do something. Hold on, I'm going to do something backwards here. I'm going to do something over here on the side. Let's see. Let me make this smaller so you guys can see what I'm doing, or bigger, I should say, from your standpoint. But it's a great question. So let's just say let's say we knew it was 2%, and we just said, how much a month should I have to pay? Well, okay, let's say, whoops, let's go by formulas. So what's where is my payment function? Payment function. So my rate is 2%. Number of periods is 36. Present value is 15. Hit OK. And that gives me $588 a month. This time you were given everything but the interest rate and said, what is the interest rate? And this is how it determines. By just if I'm using 2%, over 36 months for a present value of 15,000, it gives us 588. In this case, they gave you the payment amount and said, what interest rate will generate that payment amount so it works? Does that help?
I'm still confused.
All right.
Like,
So,
how would you write it out on paper? I tried to figure this out on paper. I solved,
okay,
um,
on paper, it's hard and it's trial and error. So let's go back to like when I said here, 2% gave me this factor. And so I could say, all right, multiplying this, I basically do a trial and error and say, okay, let's try 2%, this factor, and say equals times that factor times the $15,000 gives me $588. Now let's say I didn't know. I knew it was going to be somewhere between 1 and 5. Just guessing. How do I guess? Because I'm brilliant. Well, I'm going to go to 634. And this is where Excel becomes your friend. So let's say we weren't sure. Let's say we try 3% for, I'm going to pay 637. What is it? 36. Oh, and that's why I hate this one. Oh, yeah. 634. Give me just a minute. There's 634, 36. Oh, sneaky sons of guns. They don't give 36 on the other times. This sneaky book. They did pay attention when I was about to look up the factor for 3% to say, okay, what's the factor for 3%, 36 months for the A/P? Well, they don't have a 36. They go 31 to 35 to 40. They happen to have a 36 on 2%. Why? Because they have a problem that asks for 2%. But if you, well, they have it on 1% though. All right, cool. I'm gonna go. I'm gonna say 1%, pay 635 at 36. The A/P I'm on page is 0.0332. 0.0332. Okay. Now then, double check I got the right number. So if you try to do it manually or on paper, you have to sort of guess and try above and below to use 0 on it. Because if I say, all right, this, but this is equal to that, whoops, times, whoops, 15,000. Oops, that's up. Oh, I think I got an extra 0 out of the way. I put it's 0.0. Bear with me. This is what happens. Yep, I forgot my 0. Doing it manually, you'd say, okay, I put in 1% as a starting point. 1% gives me only $4.98 a month. That means my interest rate has to be higher. So then I go up 2% and do that multiplication. That, you have that times the amount gives me 588. What a coincidence, because that's what I agreed to during our negotiations. So if it had been over 588 at 2%, say it was 600, then I say, oh, maybe it's 1.5% is the right rate. And then I try the same calculation of the factor at 1.5%. Basically, you keep going back and forth over and above until you zero in on the right rate, which in this case is 2%. To say, okay, in order to generate $588 a month, I have to agree to 2% interest on this loan, 36 months. Did that help? Am I still confusing you?
I guess so.
No, I don't want to guess so. I want you to say, yes, I'm ready to go tell the
Well,
world.
I'm still confused why my method didn't work. I understand why that method works. But
not
I
C
tried.
method. You want to share your screen?
No, I did it on paper
Okay.
with a pencil. So
Okay.
I tried to solve like A over P. Like I solve a compound interest formula for the monthly rate
So you did
algebraically.
you did the sinking fund calculation that A equals F bracket I over 1 plus I to the nth minus 1 close bracket.
No,
No, you did the P sub A. No, the
I used
P,
A
yeah,
equals P times 1 plus R over N to the NT,
1 plus R, oh,
where
because I'm,
T is time in years and N is the number
okay, what this
of,
was, in terms of this chapter, it would be a capital recovery formula. If I go back to the end of the chapter on page 142, they give you a bunch of different series formulas of how to do the math. And so it's capital recovery because from the bank's standpoint, they want to recover their $15,000. So given I'm on page 142 under the uniform series formulas, and it's sort of, so you say, okay, given $15,000, which is your P, then you have that P against the large brackets. The numerator is I, which is 7% times 1 plus 7% to the 36th power, divided by 1 plus I to the nth minus 1. And that will give you your interest factor times your $15,000 to figure out, go backwards and figure out the right rate for that type of stuff. So you basically have to solve, in that formula, you have to solve for I, God bless you, to find it. And so that's where, on these type of things, this sounds like a broken record, I highly recommend using Excel or the tables because it's just sort of, there's so many places to go wrong arithmetically. You put your n or 1 plus n or multiply it instead of make it a superscript. It gets messy. Oops, Braden trying to get in. Well, welcome, Braden. The gang's all here now. Cool. No one will be shorted during the breakout sessions. So, that help? Or I mean, I can look at, I haven't looked through the homework yet, perfectly honest. It was submitted last night. But when I go through it, I can look through it and see how can I make, where I thought something went wrong. But right now, I can just tell you what generally I would do. But I always go and make comments on the homework. So I'll be doing that when I go through it if you're saying, I can't figure out how I got this way. But did I make any sense?
yeah, I should have used a different formula. But I shouldn't have used it at all because it would have been too much algebra.
Again, that's what I keep saying. When I was in school, Excel was cheating. Nowadays, you've learned to embrace the Excel. Or in my day, it was called Lotus 123. I'm that old. But then Excel came along, and I don't know if Lotus even exists anymore. Okay, so I'm going to move on to 420. And this is where, again, the right page, company buys a machine for $70,000, which agrees to pay for in 6 equal annual payments. As soon as you have equal annual payments, you should be thinking that A, annuity. Beginning 1 year after the date of purchase, which is everything unless otherwise, we always assume that, okay, you pay the money today, and the paying it back is going to start 1 year or one time period after. Give you your annual interest rate of 5%, but, and this is the tricky part, this is where logic comes in. But immediately after the second payment, the terms of the agreement are changed to allow the balance due to be paid off in a single payment next year. What is the final single payment? Okay, so you got basically a two-step way of thinking about this. Okay, and I use this nice little diagram here to say, here's what's going on. If you were just doing it on a normal annuity, you'd be paying your present value of $17,000 because you borrowed that right at year 0. 6 years, 5%. So that means at the end of year 1, you paid 3,349 because you put your payment amount and said, okay, given $17,000, 6 years, 5%. Excel, please tell me what the payment would be. So by the time you get to the early payment period at the end of year 2, you've already paid this much. So how do you figure it out? So, and also if you want to get that 3,300, I also did it down here using the table. You can go to the table, use the A/P, page 640, 5%, and it gives you that factor. which you multiply against the 17,000 to get the same, 3349. So that's what this part is. Now then, at this point, after already making 2 payments, we're going to start paying off. And immediately after the second payment, that means you're trying to say, okay, at year 3, I'm going to pay off the rest of this loan early in one big chunk. So we need the value of the remaining payments. So you paid one now, periods paid later. Oops. Which is, present value of 3,300 for 3 years at this time period. Because at this time period, you're going to pay off this, the current year, plus 3 years. You're going to pay them off in year 3, because it says at the end of year 2, you can pay it off early. That means, so at year 3, you're going to pay it off early. In year 3, you have the current period time owed, which is 3349 at year 3. You're not making this payment today. You've gone through time and ended up in you're in year 3 today. Because after year 2, things have changed. Cool. Well, you're going to have the current year's payment at that point in time, plus 3 years for years 4, 5, and 6. Is everyone with me on that part? Is anyone with me on that part? I have 2 people who say yes.
I'm a little fuzzy.
Okay. What they're asking to do, and this is where we spend the rest of the class, or classes, I should say, dealing with the problems. You've got the basic toolkit with all the present values and that type of stuff. Now I'm going to throw things at you and say, okay, solve this problem using all the tools you learned in chapters 1 through 4. So this timeline up here, which I'll highlight the whole thing, is what everything would have been had you done nothing. You didn't get terms that said you could pay it off early. So if you'd done that, you would have said, okay, every year for 6 years, I'm going to pay $33.49. That's this payment calculation we did. And that's the payment value, the annuity value of $17,000 over 6 years with 5% for your discount rate, as we used to call it, or interest. So if nothing happened, but we just took out the $17,000, paying it back over 6 years at 5%, we'd pay back these amounts every year for 6 years. Now then, we suddenly get a change in plans where the bank says you can pay it off early if you want. Do we want to? We don't know. But if you want to, you can pay it off early. Maybe we just inherited money from a rich uncle. Okay. Well, in year 3, if we want to pay it off all at once for the remaining loans, you've got year 3's payment plus the future year's payments to pay off. So you're going to pay that $33.49, which is the year 3 amount. But then what is the present value? If we're going to pay this off when we're in year 3, what's the present value of these 3 amounts at year 3? And that's the tricky part here. You're saying you're now in year 3 because you made these first 2 payments in years 1 and 2, borrowed the money at year 0. So what is the present value of the future payments when you're in year 3? What is the year 3 value of these 3 payments? The year 3 value of $33.49 is $33.49. What is the year 3 value of these? Well, at year 3, you have the present value of the loan minus the 3 payments, which is 3, because you have 3 remaining future payments, 4, 5, and 6. You're standing in year 3 right now. So how do you got to discount these payments back to where you are now in year 3? Well, how do you do that? You take 3 periods, which is basically your 6 minus 3 because it's a 6-year loan and you're in year 3. So you don't count this year. You're only looking at unpaid future years. There's 3 unpaid future years. 6 minus 3 is 3. So that's where in this calculation you get 3. Interest rate is 5%. Payment amount is $33.49. We know from our calculations. So the value of those 3 payments in years 4, 5, and 6 in year 3 is this $91.21. Present value of the amount, $33.49, over 3 years at 5%. And that's what this is. Put in my formula here. We can read that tiny on the screen. All I said is give me the rate, the same 5% we're using. Number of periods, I put D6 minus 3, just to show you that you can put formulas in your formulas. I could have been smart and just put 3, put that 3 in there, but I put D6 minus that 3, because if you have a formula calculation, you can put formulas within your present value, future value rate formulas. The payment amount, we know, we calculated that at the beginning. And so I said, okay, that gives you my periods paid later. The present value in year 3 of years 4, 5, and 6, plus the present value of year 3, which is the value because I'm in year 3, add these two together, and you get the total amount you would have to pay during year 3 to account for the current year's payment and the 3 future period payments. How many people have had their brains explode?
I did.
Just so you know, the answer in the book is wrong in this case again.
Did I point it out? Is that the one I missed? Let me look back. I thought I highlighted it. I have a highlighting system in my book. But I'll believe you. I believe you.
Yeah, the answer on the back of the book's like 8,000 or something.
Oh,
Yeah, this problem took me like 2 hours just because.
that's why you should never trust the back of the book. All right, 420. Make sure you get the right problem. 420. Oh, that's bad. Bad. That's why I should never sign. Problem is, I always get requests to sign ones with the back of the book. Again, I apologize. This is a new edition. I did go through everything, the homework for this week's that's due. I missed this one. So yeah, so this is where you're doing this time period. That 8,000 is wrong. It's 12,000. So have confidence in yourself if you keep getting it. Or shoot me an email after the 4th or 5th time you try to do it and it doesn't work.
Professor, I
Yes.
did the same problem, but in a different way, and I got the same answer. And looking at it, your way makes more sense. But I want to, like, I'm curious to know, like, what I did, like, how that works. Because I used future value like 2 times, and then it worked out.
You use which value?
Future value. So pretty much what I did was, so I found a yearly payment, which was same as you, right?
Mm-hmm.
So then I multiplied it by 2 to get how much I have paid so far.
Mm-hmm.
Then, let's see, I found the future value as the amount left after 2 years. Let me see how I got to that.
Future value amount left after 2 years. I'm not saying you're wrong. I'm just not following completely.
I did this like 2 days ago, and now I've already forgotten about it.
I mean, if you want to share your screen, we can share your screen, or I can look at what you did and.
I'm using my other computer, but
Okay. All right, no worries. Oh, good question on that. Do we not need to include interest from years 1 and 2? That's years 1 and 2 is gone in the future and past. We don't care. It's a sunk cost. We ain't getting 1 and 2 back. We're in a new world order starting in year 3. These 2 years are gone. We paid them, and it tells us, because it says immediately after the second payment, meaning your terms have changed, so you can be paid off in a single payment next year. So next year, you're doing a payment from this time period. It tells you you're after the first 2 years. States that's where you know you're no longer in year 1, year 2, you are in year 3. And you've already paid that much down on the loan.
So once we get into year 3, how do we know how much is left on the loan?
Well, you
Because
know,
the way
actually, it's not how much you have left on the loan, although you could argue, you know, in this type of problem, the total loan, and this is where interest works, I just highlighted all the sums. You're borrowing $17,000. I don't know if anyone can see the tiny, let's do something, let's do the old fashioned way. Hit sum. The loan is $17,000. The amount you're actually going to pay is $20,000. So the interest over the entire loan would be 20,000 minus. So if you didn't pay off anything early whatsoever, for the sake of argument, then the amount of interest on the entire loan would be $3,096. So that's what you would have paid. But
I did mine a little bit different. I can share my screen if you want, just to see a different way.
I'll stop sharing and then so you can share. All right. Theoretically, you should be able to share.
You're still sharing?
I'm not sharing anymore.
It says you cannot share your screen while other participant is sharing.
I said stop sharing.
Oh, there
Let's
it goes.
try again. All right, now try.
All
Hit
right,
the
give me
button.
a
It probably
second.
hated me. I hope it didn't say stop recording.
So what I ended up doing myself is I ended up getting the correct payment per term, and then I doubled it because of the 2 years, and then I subtracted them from the present value or from the original loan value. I'm wondering if that was... I didn't get the same answer as the things. I'm assuming it's because I didn't count for the interest.
I did something similar. You have to find the new present value of the loan because the whole
So this is
thing
what
has
I did.
accumulated 2 years
I figured
interest.
I found the payment first, and then I just figured out what the value of the loan was after you made the
Okay.
second payment. And then to figure out what the third payment would be, I just did 1 year of interest in addition to the second
Okay.
year
I see what
value.
you did. Yeah, that works.
Yeah, so I just
Again.
figured after you made that second payment, how much of the loan is still left, and then a year from then, how much additional interest has been added to the principal,
Yeah, that
and
works.
that's how much you have to pay.
Again, just because you didn't do it the way I did it doesn't mean it's wrong. Maybe you got the right
Yeah,
place.
this is how I figured out. I mean, I just did a future value after 2 years.
Okay. I see what you did.
That's exactly what I did, but I wanted to know what's your reasoning behind doing future value on that one, on the 11,000.
So I just wanted to know after 2 years, what is the value of the loan? Because
In one
then,
sense,
well,
oh, sorry, go on.
I just wanted to know what the value of the loan was after I made that second payment, because that's how much I would still be needing to repay. And then if I wanted to pay all of that at year 3, there's going to be even more interest that was added on. That's what this calculation is down here.
Right.
And
So the future
oh,
value for at year 2, that means how much is left on the loan.
Yeah, so I made 2 payments. Now how much is still left to pay?
Okay.
and one of the, and I hesitate to go down this route because it tends to get confusing. But when you're discounting the 4, 5, 6 years back to year 3, these technically, yes, the 3349 is part principal and part interest, but you're discounting both back to year 3 because they're combined in this amount. So yeah, part of this 3349 is principal, part of this 3349 is interest. And they do have a table. I don't think I went into that in detail last week on where they have a payment series, how you do that on how much is interest and principal every month. It's how mortgages and car loans work. But, oh, I'm pointing to my screen like you guys can see it. I'm gonna share again, hold on. So you can actually see what I'm talking about. All right, so these future years, every payment here includes interest and principal. And that's where you can say, look, of the total loan of that, when all 6 years added up, is this $20,096. This $3,096 is allocated amongst all these years. So it's in here, it's in here, and it's in here. when you discount year 6 back to this year, you're discounting both the interest at that period and the principal together. Because they want to know what the present value of that interest and principal in this year. So you don't have to worry about including interest. This is, again, this has been paid. You're saying, what's the present value of this future principal and interest? And that's what we're doing. Again, I got that people are asking kind of that question. I don't like to go down that road because it tends to offer another point of confusion. But technically, each one of these values has principal and interest in it combined by definition. Does that confuse you even more?
So what you're doing essentially is ignoring year 1 and year 2 and counting it as a 4-year loan?
Well, in one sense, you could philosophically no, but by doing the math that way, you get to the right spot. These 2 years are paid off. Gone. You're never going to get them back. So you're saying so at this point in time, I have a current year payment and 3 more years of future payments. You can pretend like these never happened. These 2 years are only here for the purposes of calculating that 3349 at this point. Because this was your payment plan, 3349 every month. These are paid, and you're now in the future, year 3. So I have this due today at the end of year 3, and 3 more payments for 3 years. If I want to give you the equivalent at this time period of these 3 future payments, you got to discount these back at the 5% they give us, 1, 2, 3 years.
Is there any way you could calculate it as all 4 years together instead of splitting it up to 3 years and 1 year like you did, or no?
Let's see. Because if you were at the end of year 2, yes. Because it states that we have to pay at the end of year 3, no. Because you're at the end of year 3 and there are only 3 years left on the loan. You're at like December 31st, year 3. Year 3 is all passed, and so you're paying that present value here. You got to pay January 1st, year 4 through December 31st, year 6. So you don't have
one
to discount.
One thing that I was getting confused on looking at it, so the way that I look at most of these problems is that we're spending, there's so much on interest, so much on principal, and that amount changes as the years go by. And the only reason our payment is set at this point is because they totaled up the total amount that we're going to have to pay back, and then they broke that amount up. But we're not paying an equal amount on each month. Are we?
When you say equal amount of what?
When it goes to the principal versus the interest
Oh yeah,
rate.
principal and interest, no. When you do a loan schedule, as they had an example of that in chapter 4, no, you're not. Over time, the interest amount is diminishing. But it doesn't come into play in this problem because you're not agreeing to pay necessarily, you're not paying the full $20,096 back that these add up to. You're paying the equivalent after the first 2 years of that amount. So dollar-wise, it's not going to add up to the full amount of principal and interest. You're getting these payments. What's the equivalent of this year's payment plus the future payments? What's the present value equivalent of these 3 future payments at this time period?
So we're okay to do it like the one guy did, where we summed up just like you did. We figure out what our payments are going to be. We pay those first 2 years, and then we can just subtract that total amount from the first 2 years from the original loan amount, and that will give us.
If I hear you right, and correct me if I'm wrong, it's kind of like you're trying to essentially do a mini interest and principal calculation. Sounds like, as you're describing it, and if I'm mischaracterizing it, let me know. But that's how I see you philosophically doing it.
Mm-hmm.
You can do it that way. It's more work than necessary, quite frankly, because you got a flat payment amount that you're, at this point in time, after the loan has been set, you agreed to pay this per month.
Mm-hmm.
When you go negotiate a car loan or mortgage, the interest and principal are basically ways of getting to an annuity payment. And then once that comes, the bank, yes, if you're going to settle it, and this is where banks don't have to, but you can do some calculating and say how much principal is left. And a nice bank might let you renegotiate on the principal.
Couldn't you just do a future value calculation at year 3 and get the same answer?
Say, what is the future value of?
If I said with that payment of $33.49, 5% interest, what's the future value at the end of year 3?
The future, I'm not
So the
following.
present
Help
value
me.
is $17,000. The future value at year 3, given the $33.49 payment, wouldn't that be $12,470?
The present value of $17,000 at year 3.
No, if the present value at year 0 is $17,000, the future
Yeah.
value at year 3 should be $12,470,
Yeah,
which is the answer, right?
yeah.
So couldn't you do that to get your answer?
I just did it on Excel and it came up as 9,120.
That 9,120 is down here on my spreadsheet, and that's the equivalent value of the 4, 5, and 6 years at
Yeah,
year
that's
3.
the future value, but you haven't paid your $33.49 payment.
In year 3?
Yeah, so he got the value at the end of year 3, assuming you paid
Yeah.
that payment.
If you pay year 3, and you pay your end of year 3, you write your check for $33.49, then you write a second check to cover the year 3 value of the 3 years that you haven't paid yet. So you discount the 3 years, 4, 5, and 6, a 3-year annuity essentially, and discount that back at 5% to get the value of those 3 payments you're not going to make in year 3. That gives you the 9121 or 9121. So that's the future period. For the periods paid later, as I put it on my example here, I call it periods paid later, meaning that's what you would have paid if you didn't cut it off early. And then you add that to the one you pay, that is this $33.49 is year 3 for year 3. This 9121 is years 4, 5, and 6, paid at year 3 at the same time you pay off the current year's payment. So you're paying, when you pay off that $12,470, you're paying both the current year's payment, that year 3, 3349, plus the equivalent value of the future years that you're not going to pay because you're going to pay them off now instead of in the future. There's a stunned silence.
This problem just seems a lot more complex than I gave it credit.
I mean, in one sense, it is, and that's probably what they're trying to they are throwing sort of a lot of words to you. I mean, the equivalent thing that they could say, okay, hey, if we wanted to pay, if we were going to pay, I'm going to do something. I hate giving these analysis examples because sometimes I take people who understand it and then they suddenly say, oh, until you give that extra example, I'm now more confused. But think about backwards, you'd say, okay, if you agreed to pay $3,349 for 4 years at 5%, the present value of that would be $12,470. 3 successive payments. So if you were right here, no, it's not going to work. You had to pay something off back. Actually, this is how loan sharks work. But loan sharks, when you borrow money, your first payment is made at the time of taking the loan. This is a loan shark loan where you say, okay, interest starts at immediately, and your payments due immediately. And I hate to say it, but people get confused more. When I told you to ignore that type on present value and future value, type 1 is what we normally do, is assuming the payments at the end of the year. If we assume now we're going to pay at the beginning of the year, well, okay, you're borrowing at the same time that you're paying your first payment. So if you're paying right away, January 1st instead of December 31st, then the present value of those 4 years will be $12,470. That may be, again, that's something that may say, oh, I understood it until you gave that example. But sort of these are sunk costs, if you will. You paid them, never get them back. What you do know is that you're contracted to pay this amount every year for 4 years, and you're right here, you kind of forget these first 2 years and just say, okay, I'm now here. I've got this value to pay and 3 future value payments to pay. Discount 4, 5, and 6 into the present day, which is 3. Oops. And that's how you get your 12,470. How are we doing on this one? No one wants to speak. Okay. Hearing no more objections, I'm going to move on. So, for the 425-2, go way up to chapter 5. This is your lead-in one for the next one, which is you have all the tools to do this at Flossie. And income from a rented house. Let's see, wait, 5-2. Let's see. Income from rented house is $26,400. And expenses are $7,200. If the house can be sold for $255,000 at the end of 12 years, how much can you afford to pay for it now if you considered 8% to be a suitable interest rate? Considering they're below 3% now, it wouldn't be. But let's go with it. So you have rent every month, the $26,400, expenses of $7,200. That gives you a net income of $19,200 every year. So what's your time period? 12 years. Interest rate, 8 years. The payment, the amount you get every month, the annuity essentially, is $9,200. You just calculate it there. In the future, you're going to sell it for $255,000. That's your future value. How much can you pay for it now? That's asking what's the present value today. So you use this calculation where you say, you have the rate, number of periods, the payment we calculated, $19,200, and the future value of $255,000. We're going to pay for that in the future. So for that period, what are we willing to pay for it now if we consider the interest rate the right way? That means we'd have a present value of $245,000 today, or 246 rounding. So future, they give you the future value, the interest rate, and that's why I start using this again. The book uses this all the time. You start off a problem by just sticking what you know into this little formula they use all the time, or this setup. We know you had to calculate the payment amount, being the amount of income you can get every month. End of that time period, you're going to sell it so you can move to your condo in Barbados. So you think you'll be able to sell it for that much. How did they come up with that? You just guessed. You looked on Zillow and said, in 12 years, it's going to be worth that much. So what will I pay for it today? Well, it's going to be present value. Every month you're going to get that, or every year you're going to get that. You're going to sell it for that. In this case, the future value is almost like the equivalent of a salvage value we use in problems. At the end of it, when we're done with it, we're going to get $255,000 in the door. After receiving this every month, our salvage value or future value is $255,000. So our present value that we're willing to pay for that house today is at $245,957. That makes sense to anybody?
Yep.
One says yep. I hear one yep. Everyone else is confused as heck then. Go to 3 people say yep.
Okay.
I think that's the, I give up. Let's just get to the lecture part.
Well, I ended up actually setting it up correctly, but for some reason I got lost when I all of a sudden wasn't getting the numbers to line up even close to what the back of the book or what I thought it was going to be. And I just realized what it was. I accidentally put a negative somehow into the present value function, which changed the entire equation.
Again, that's the key we've talked about before. Getting your signs right. You know, I won't mark you right or wrong if you made the payment negative and something else there. It's sort of, as long as you're consistent, payments going out one way and in the other way have opposite signs. That money you're getting in, I mean, I try to do it from a standpoint of the person the question's asked for. So if you're an individual who's buying a new lawnmower for $200, well, that's money you're paying out. That's negative. It's no longer in my bank account. It's negative. On the other hand, if that lawnmower saves me money on hiring a gardener, for $50 a month, well, then that's money I'm saving. I'm getting it in. So the payment out is $200. The money I'm negative $200 going out, but $50 a month coming in from the savings of not hiring a gardener. So that $50 is I'm getting every month from savings is positive. $200 I pay for it is negative. You do the opposite, I don't care. You're doing from the standpoint of your credit card, fine. But getting the inflow outflow declarations, as long as you're consistent, your bottom line number will come out the right way. The book tends to use, as I do, payments going out are negative, money coming in or savings equivalent coming in is positive. All right, let's close this and get back to our cool PowerPoints. Oh, homework took an hour. That's obnoxious. Whew. Okay. Now
I think
then,
most of that was spent on the 421.
yeah, it's a tricky. And again, the problem that one wasn't the math; it was the logic. And you'll find that going forward. As I said before, we've gone through most of the tools that we're going to use in this book. The types of calculations of time value for annuities, present value, single payments, multiple payments over time. It's getting your mind right now. It's going to be the issue on problems, saying, what are they really asking me? And where am I? And what pieces of information can I ignore? What pieces of information do I need to concentrate on? That's going forward really what the second half of this class is all about, just not new techniques. You've got the toolkit now from the first 4 chapters. You now got to figure out how to build a house with the toolkit you have. We're going to save that for next year. That's a good way to talk about it. Okay. So, stuff in this chapter, economic analysis problems, time period analysis, multiple alternatives, applications, and complications. And that's what it's all about. So, here's where we get into the present value. And we'll go back to that, I can't remember who it was. Was it Jake that asked me that question about what net present value is philosophically versus present value?
Yeah, that was me.
Okay, present value and net present value. So here we have income stream. We paid $30 out in year 0. And in years 1, 2, and 3, we've got $20, $20, and $30. We have uneven amounts. So it's not an annuity. We can't use one of those P/A or A/Ps or F/A because we have uneven amounts. So what net present value as a function does is say, highlight all 3 of these years plus the interest rate, and it will give me the value of these 3 payments at year 0, which I then add that against the $30 that I paid out in year 0, and that gives me the net present value that they've labeled here, $29.48. Now then, an alternative way of doing this problem without this net present value function would be to say, okay, what's the present value of $30 at year 0 at 8%? So you go to your table at 8%, look up 3 on the 8% page, and discount this year back to there, then discount this year over 2 periods back to year 0, and then year 1 period back to 0, add those 3 present values together, then offset against 30, and you have a net present value. Both the function and the individual present value calculations get to the same part, technically, of net present value, but it's saying the present value of all the future incomes and outcomes added against the outcome in years 0. That's net present value. As a function, it's wonderful. You can just highlight this and it'll give you the value of any uneven income stream right away. That's why it says B3, the year 1 output, plus the present value of B4, 5, and 6, that range of the future payments coming in, and that gives you that $29.48. The alternative to using net present value on uneven years is to discount each one of these one at a time backwards to get the present value at year 0. Does that make any sense now? Or am I still off?
Sounds good
It
to
kind
me.
of makes sense. I understand like the mathematics behind it. What I don't understand is the logic when I would decide to use net present value.
Basically, it's anytime you want to know, and again, this is where does an investment make sense? Okay, you're just saying, hey, I'm going to pay $30 for a used lawnmower. I'm going to save this much every year by not hiring a gardener, because he would have raised his price in year 3. Because the function net present value is saying, okay, given I'm going to get these future amounts in the future, is it worthwhile today? If the net present value is 0 or less 0, it's break even. If the net present value is less than 0, you're losing money on that investment. Don't do it.
So this is basically saying over a 3-year period, you're going to make $30 by buying a $30 lawnmower.
Yeah. If it tended to be negative $29, then you say, whoa, I'm better off paying the gardener. And that's basically trying to say, is it positive? If a net present value is positive, it's an investment worth considering. If it's negative, okay, you're going to lose money. Don't do it. If it's
Yeah,
equal
that
to
makes
0,
more sense to me.
yeah. If it's equal to 0, then, well, how much do you really want to do the garden and save money? 0 is the break-even point, and when net present value is 0, the internal rate of return is whatever interest rate you use to calculate. But don't go there for now.
So
Now
the
then,
net present
oh.
value is for determining like problems with cash flow where you have money going out and you have money going in.
Yes,
And
generally
present
yes.
value, and present value is for problems where you're dealing with loans and interest and you want to find them.
No, present value is for both. The function net present value uses, when you use the function net present value, it takes the present value of each individual item. So you can use present value in this problem too. You just would have to make 3 calculations instead of 1 on Excel. Present value can be used anytime you need to know the present value of a future payment. It might be 1 future payment in 10 years, or it might be individual payments over the same period of years. For example, I mean, one of the reasons we use the annuity function and came up with that summation series, you know, you can use present value function to determine an annuity. You just have to do a separate present value calculation for every year of the annuity to find out what it's worth today or what it's worth in the future. The mathematical formulas and Excel formulas were developed so you don't have to do an individual present value calculation for every year of an annuity or every year of a loan or every year of a payback project, if you will. So the math, you can do the math either way. They're trying to say, okay, because what behind the scenes, this net present value function is using the present value function 3 times. Once for year 3, once for year 2, once for year 1. Behind the scenes, all it's doing is doing a shortcut, so you don't have to do it present value 3 times. That's what's going on behind the scenes in the programming. It's still present value calculations. Make any sense?
Yeah. So when you use it, whenever you're buying something, you put the buying as 0, and then you do minus first. You do minus for the stuff you're buying, and then for adding, you put it as positive, and then that's when you select the range. The range don't go through the initial.
Yes, and this again, net present value. You got to make sure you get your signs right. Again, if you want your outflows to be negative and your inflows to be positive, or vice versa, it doesn't care. You just need to make sure you're consistent on it. That's why I say in year 0 here is today, and I paid $30 for my used lawnmower. Then next year, month, year, whatever, I'm not gonna have to. I'll save $20 because I'm not paying the gardener anymore. Okay, and then year 2, I'm saving $20. Year 3, I'm saving $30 because I said I thought the gardener would be putting his prices up in year 3. Okay, so these 3 years of savings, and so you highlight those 3 years, and the Excel behind the scenes does a present value calculation for this $30 back to year 0, $20 back to year 0, $20 back to year 0. Behind the scenes, it's using the present value math. It just creates this nice function to save time and effort. Again, if this was an annuity, you could still use net present value if it was the same amount every year. Even the annuity is using present value, over and over and over, because it's cheaper to use the same algorithm over and over and over inside behind the scenes in Excel than rewrite it. It just says do it once for every year. All right, now I'm going to move next. Rest of this lecture, I'm going to go over examples. I may stop at 4:30 and see if anyone wants a break, because it's taking a long time. But these are interesting things. Now then, I'm using, I address on this example on 5.1. I get the right page. So I can look at it. Hold on, going to 5.1. And it's basically trying to say, how do you compare two things that have the same lifetime period? Now then, the book uses this term gradient and has a formula for gradient. And you look at the back of the book on the nice little tabulation pages, it has gradient. In fact, it's the last two columns. And there's a reason the last two columns, because no one uses it anymore. But it's in the textbooks, and it was invented by mathematicians about 120 years ago, because you need a quick way to calculate something that changes in the amount every year, but changes the equal amount every year. And that's where in this example we see, and it came up before another problem, but I don't focus on it, because when you have wonderful things like net present values and other present values, it's something else to learn and forget and make mistakes on. But it's an unnecessary, well, as soon as I say that, some mathematics professor or finance is going to say, no, what about this? And I'm wrong. But in my experience and career, I've never had useful need for the gradient calculation. It's meant to do things like device B. We have 0 to 5. And every year the amount coming in increases by the same amount, called $500. Well, they developed a summation series, allows you to do just like an annuity, when it's the more complicated calculation. As long as it increases by the same amount every year for the entire year of the study, you can use this calculation. That means you don't have to use one calculation for this, one calculation for this, one calculation for 4,000, one calculation for 4,500, one calculation for 500. In the modern world, net present value calculations on spreadsheets and statistical software make the gradient irrelevant. You can use net present value instead of gradient on this B calculation. So basically, we're trying to get you down there. We're trying to dig you down the road. How do you make comparisons between two projects throughout this chapter? They both have 5 years. One's getting $3,000 a year for 5 years. One getting a different amount for 5 years. One starts off with 10,000. One starts out with 13,500. Okay. Negative, the present value, they say worth, but remember, present value and present worth, for purposes of our class, teach as the same. They're the same as far as we work. So you say, what am I talking about, a present worth or present value calculation? In this class, we won't differentiate. They're equal. If you want to get your PhD in finance, then we can start discussing the philosophies about why they're not. Okay, so you take your $10,000 outflow, $3,000 you're getting present value of an annuity from the 7% page, 5 years. Get your factor, gives you $2,300. Cool. Or you can say 13,500 plus $3,000, your starting amount, plus a gradient of $500, meaning that gradient is, it starts over here, and 500 plus an extra 500 on top of that, plus an extra $500 on top of that, plus an extra $500 on top of that. And that's what this function does. I don't like the function, but I teach it because you have to. So when someone says it once, we'll say, I remember that one twit at OIT who told us how to do a gradient. So outflow 13,500, present value of the annuity, because buried inside each of these numbers is a $3,000. There's $3,000 in that 3,500. There's $3,000 in that 400. And the gradient function says, okay, I'm going to increase that extra amount every year to give you the equivalent. 2624. Cool. Now here's what I would do. Okay, here's the gradient factor they get. It's in that 7% page, just to show you what they did. You got your annuity amount, you got your 4,100 here. That 4.1 is that 4.1 present value of annuity down here. The gradient function comes from there, 5 years. That's 7.647. Is that 7.647? That 4,100 is that 4,100. So we're getting the present value. Our outflow, our negative amount is 13,500. Inflows of $3,000, our starting amount, plus the $500 that gets increased every year. Right there, give you 2624. That's where they get their numbers from on the gradient. It's on the table. Now then, for my spreadsheet solution, here's what I did. Instead of using the gradient, I did net present value. I basically just said, okay, 2,301. I highlighted these with net present value, 3,000, 3,000, 3,000, 3,000, 3,000. Then got the present value of that. And I will stick it up here so everyone can see what I did up close. This is on the spreadsheet, on the PowerPoint view selection. So here's how I did that exact same problem. I don't care about the gradient because it confuses me and I don't want to have to ever learn it again. But in both cases, exact same problem where they had to use gradient and the annuity on the other one. Both cases, I can use net present value. I basically highlight these 3,000s and then add the $10,000 at the beginning here. That gives me my 2,301. The exact same formula works for this uneven amount because it's net present value. Once again, for this calculation, I highlighted these with net present value formula. That's that E4, interest rate of 7%, E8 to E12, the range, starting at year 1 down there. Let that calculate itself, then add the year 1 to it. And that gives me the 2624. To me, that's so much nicer than worry about gradients and the annuity. I just have to remember one thing, net present value. If you want to do it the other way, it's fine. If you want to do a present value calculation for every individual year, you can do that. But once you learn net present value and the right circumstances to use it, it's so much simpler than doing it the way the book did. Just for peaking interest, I put internal rate of return here. We're going to have a whole chapter. I can't remember 6 or 7 on net present value and IRR. But I'll give you a teaser here on this calculation. Just put this here just because according to net present value, which one should you choose? Someone shout out the answer. But net present value, which has the better net present value?
B.
B, fantastic. Which one has the better internal rate of return?
A.
Thank you. Thanks for playing. Appreciate it. This is the trickiness when we start dealing with these things. I'll have a whole chapter on this. The two most common ways of measuring things for project evaluation, net present value, internal rate of return, and they frequently differ. So how do you choose between the two of them? Stay tuned. So
in our book, when we have something where there's 2 options, then we should use net present value and internal revenue, whatever, to find out which one's better.
The trickiness is that there's never, first off, and philosophically, internal rate of return is one of the more useless calculations out there because it doesn't tell you a lot, but it's used because it's easy. To calculate this internal rate of return, you just highlight everything, including the outflow. That's a big calculation difference to remember. We talked about this in, I think it was the end of chapter 4, we went over this. IRR, you highlight the whole thing with the function. Net present value, you highlight the outflows and offset the year 0 against it. How to choose when they disagree with each other is a whole other matter that you have to deal with cash flow requirements, length of term requirements, and what else could you do? They disagree more than you think in the real world. And IRR is easy because a company can issue a policy saying, we won't invest in anything less than a 14% return. Well, okay, if that's your philosophy though, then you're missing out on this project which would have paid back more money. Why is 14% your agreement? It comes up because, quite frankly, I know we're going to go long on this lecture tonight, I apologize. Most people view respectable rates of return in terms of what they call their cost of capital for the company. They look at what it takes to borrow money, what their stock investments are, and what their current returns are on existing things like money in the bank. You have $1,000 in the bank for this, $1,000 in the bank at one rate. So the average of those two gives you a rate. You get 6% interest from your loans. You're getting 10% interest for your stocks, 50% of money's in stocks, 50% of your money's in loans. So you take half of each rate, and that becomes your required return. If you can't beat the stock market, we don't want to do it. It's one of the most common and one of the most short-sighted approaches, but it's there. So you got to know it's there because it'll come up in the real world. But anyway, I'll save more time. So 5.2, we're now talking about useful or equal. Build a full-size facility now, and we've got two projects here. One is we're going to build this nice construction factory. It's going to cost us $400 million today, and we can build it. Or we can build a smaller one today for less money, but then in 25 years, we're going to have to expand it for what we think will be another $350 million of that times dollars. So at which, and we have 6% interest, which should we choose? So ultimately, all these decisions comes down to, throughout this chapter, getting everything in a today dollar value. So you can say, we're going to spend this much now, this much in futures coming back to us. We try and bring it back to today's dollars values. So that gives us equivalence that we keep talking about. What's the equivalence of $400 million today compared to the equivalence of $300 million today plus $300 million in 25 years? Well, present value of the first one is easy. It's today. We can spend $400 million today. No calculation necessary because it's today. So the cost of the first one is $400 million. It says so right now. Or we can pay $300 million today plus $350 million 25 years in the future at 6%. Well, you look up your present value of a future value of 6% 25 years and multiply that against your $350 million. And that gives you your $381.6 million, adding to $300 million you're going to pay today. So $381.6 million. Which one is less? Single stage or the two-stage construction? Anyone? Anyone? Can you guess? No one?
Two-stage?
Pardon? Yeah, two-stage.
Two-stage is less?
Yes. Last time we checked, $381 million was less than $400 million. Cool. Now then, here's how I did it in Excel. This is what they showed in the book, but I typed in, we had the $300 million. I said $350 million in the future, and it's 25. I had 6%. I threw it into this calculation, and that gives me that 81.549. Again, you don't need to do calculations on the two-stage $300 million paid today, because it's today. You don't have to do calculations on the $400 million paid today, because it's today. What you need to know is the present value of that $350 million you're going to have to spend 25 years from now to expand a factory. You add that, so you get $381 million. And again, as I just said, $400 million is greater than $381 million, so we choose the two-stage thing. Everyone with me? Because it's about to get more complicated. Hearing no objections. All right, now different lives. And there's a couple of different ways of doing it. One of them I'm going to show you, which I don't like at all, never use it, and I think it's deceptive. But I'll show it to you because it's in the textbooks, and I do get people doing it out there, even if I tell them not to. So what happens when you have two projects you're trying to evaluate? They don't cover the same time periods. There are different techniques you can use. So here's the thing they got. Pump A and Pump B. One has a 12-year life, one has a 6-year life. What do? Well, as in all things, you got to figure out the present value Now then, what's the present value of pump A? Well, they give us an example 5.4, and we're now on page 165. Okay, cost you $7,000. That's your year one. Now, salvage life is $1,200. At the end of 12 years, you can sell it for $1,200. Well, you got the cost out now. You're going to get $1,200 back at the end of year 12. Cool. Well, you put it in math. Future value is $1,200. The present value of that $1,200 in 12 years is $533. So the net value, or you say net cost, if you want to say, $7,000 outflow, $533 at the end of 12 years. We get $6,467 essentially is the net cost of these two things. Cool. Alrighty. That's the first option. Pump B, however, has a different thing. Pump B has half the life of pump A. So how do we say what's the equivalent? How do you make equivalence happen on these two things? Okay. Now then, well, at the end of year 6, they assume that you're going to be able to reinvest for the exact same stuff it cost you for the first 6 years. So basically what you do is you take the first 6 years of pump B, which was $5,000 out the door and $1,000 salvage value, and you basically tack that exact same thing on the end of the 6 years, for the first 6 years, to make it into 12 years. And when you do that, you have to discount the extra salvage value, because you're already going to, you have a salvage value still. You're assuming you can pay out the door at $5,000 like you did at 0. You have $1,000 salvage value. And so you have to do a 2-step process. You got to discount the $1,000 at year 6, because you're going to have to sell the machine and buy a new one, back to year 0. You're going to have to discount the $5,000 you're going to have to pay at year 6, back to year 0. And you have to discount the $1,000 salvage value in year 12, back to year 0. Whew. So, how I did it in Excel, our usual 7%, 7% everywhere. Pump B. So, part 1, cost now, $5,000. Salvage value of future value, you're going to sell the salvage value in 6 years, and in 6, you're going to sell it for $1,000. The present value of that $1,000 salvage value is $666. So the first part of that is $5,000 outflow today. The present value of that inflow for selling the machine, cost now negative, money back at year 6, $666. That gives me a net value, or you can say cost of that negative cost or negative value of $43.34. Because I've got to have a 6-year time period. I've got to treat it though it's just by itself. Paid $5,000. At the end of 6 years, I get $666 back for selling the junk machine. The second part, because you're going to tack on and assume that you can do exactly what you did today in 6 years, for the same price, same salvage value, everything. So, well, the present value of the next purchase. Basically, in 6 years, after the first pump wears out, you're going to have to go out and buy a new machine for $5,000. In the future, after that 6 years, they're up, you're going to have to pay $5,000 for a brand new machine. The present value of that $5,000 out there is $33.32. I use a present value function, which I'll pull up in a minute. And the salvage value of that $1,000 I'm going to get not at year 6, but at the end of year 12. So remember that timeline. I have 6 years for the first machine and 6 years for the second machine. I paid the same $5,000 to buy it, the same $1,000 after I sold it at the end of 6 years. So part 2 is that second year or second set of years. The present value discounting that $1,000 I'm going to sell the second machine for over 12 years. Because remember, at the end of the, getting it back to 12 years, I had the first 6 years on at the $5,000 machine, another 6 years of $5,000 machine, selling the same $1,000 salvage value. The present value of that is $444. So there's a part 2, and what we're doing here is going backwards. Because remember, we did this part. Now we're doing this part here. So that second machine to fill up the rest of the 12 years is 2,888. So the cost of both is that 4334 for the first 6 years, plus that 2,888 for the second 2 years, which gives me 7,221 overall. This is where you say pump A is better because 6467 is less than the cost of pump E, 7221. Does everyone know what we did on this one?
So what if you were to invest however much you didn't have to spend on pump A on the first pump B into like something with interest?
Well, I'll tell you, that's actually a good question, but I'm going to hold off going into that because that's exactly where we're going to end up going. And those are the decisions you make. And that's where I talk about what the cost of interest and capital are. What could you do else with the money becomes the decision in economics. I can do this. In this case, you only have 2 choices. You do pump A or pump B. You don't have the luxury of getting stuff. But in the real world, say, well, can I invest in this new factory or do I buy GameStop stock? Which is going to get me a better return? Do I hire 10 more employees to work faster? Or do I invest in a new widget that can do it automatically with robots? Those are the decisions you make in economics. So it's a great question. And we're going to be doing that question over and over is the what if? Do we do this or this? What's the better return? Because some cases it is, do I do nothing and put my money in stock or the bank or some investment? Or do I actually go actively forward with some investment in infrastructure like these pumps? But that is the perfect what if question you asked. That's what you do in the real world out there. And that's why we have an economics for engineering class. But awesome question, you're going to the right place. Now then, here's example 5.5. And my disclaimer, if I sound disdain as I describe it, I don't like this methodology. I think it's unfair, unuseful, and I campaign against it when people hire me. But it gets done. So it's saying, okay, when you have 2 projects that have unequal years, again, you're always trying to get, so you make a decision between the 2 of them, and equivalent analysis. As the book keeps talking about equivalence. So we have one alternative, different initial costs, different salvage values. One has a useful life of 7 years, one has a useful life of 13 years. So up until this last thing, where estimated market value end of 10 years, the previous problem was just like this, well, this last item here. And what they do is they say, okay, philosophically, we're just going to analyze it, assuming they both are 10-year projects. Because after 10 years, who knows, we're going to retire, we'll sell everything, we don't care. So how do you make these 2 alternatives into an equivalent number, given the interest rate they give you, initial outflows? How do you equate these 2? And there's a very complicated multi-step way to do it. And the book does it. So now I'm on page 167 if you want to go through this. So bear with me. And if I sound biased and disdain as I describe it, it's because I don't like it. But it's out there. You need to know it's out there. So what you're trying to do is basically say, how do we equate these things? Or alternative 1. Remember, alternative 1 is $50,000 out cost, salvage value cost. So you got initial cost, present value is $50,000. Or negative 50,000 because you're paying it out. So that's where we get 50,000 on this second line. You have $50,000, or down there. You have salvage value at the end of useful life, a future value at the end of 7 years. How do we know 7 years? Alternative 1 says 7 years. 50,000 initial cost, salvage value, end of useful life. Useful life is 7 years. Market value at the end of 10 years is 20,000. So you get your useful life is 7. Interest rate is 8. No payments. You got a future value for the salvage value. In 7 years, you can sell it for $10,000. The present value of that $10,000 over 7 years, 8% is $58.35. So now then, you have, that's the first salvage value. Next salvage value is that $20,000, because it says at the end of 10 years, which is the study period, is $29,175. That's why you have 3 calculations. Initial cost, no calculation. Salvage value at the end of 7 years, $58.35. Next salvage value at the end of 10 years is $20,000. So that plus that plus that is $64,000, because you're going to have to purchase at the end of 7 years, you're going to have to purchase another machine. Now this is where it gets tricky. You have this $29,000 is the second machine you're going to have to buy because you're studying, as stated up here, over a 10-year period. You don't have a 10-year period. You have a 7-year machine. To make it last 10 years, at the end of 7 years, you have to buy a new one, because you want to have a 10-year period. Why 10 years? Because management said, we're going to operate this plant for 10 years, then I'm selling it out and going home. Fine. Initial cost, $5,000. At the end of 7 years, you have a salvage value of $10,000. So the first 7 years basically is this. Actually, I shouldn't say salvage value. I should say, never mind about that. But so you have 50,000 today. At the end of 7 years, you sell it for $10,000 and you get $58.35. Now then you're going to have to buy a new machine after 7 years, because remember, you got to have it last 10. You only make it last 10 is buy a new one. Okay, so you buy a new one for $29,000, because the present value of $50,000 in 7 years is $29,000 today. Say it again. This $29,175 is the new machine that has to be purchased for alternative 1 at the end of 7 years, because you're demanding it have a 10-year life. Now then, so, and they tell you up here, the market value after 10 years is $20,000. So assuming after 10 years, you're going to get rid of it. So, present value of that $20,000, you're going to sell that second machine you bought for $20,000 in 10 years, discount that back to get $92.64. Because you buy a new year for year 8, you're not going to use it the full 7 years it's capable of being used. You're going to sell it at the end of 10. So that's why you get this total value, negative value or cost of $64,076. How are we doing? Hearing no murmurings, I'm going to go forward. That's alternative 1. Alternative 2, well, that's a little easy. Alternative 2 is 13 years. And at the end of 10 years, they give you $15,000. Okay. So the future value, you have a future value of $15,000 because they told you that's what it's worth at the end of 10 years. The present value of that $15,000 10 years from now is $69.48. You paid $75,000. So that costs you $68.52. So essentially, I'll pull up my marvelous spreadsheet. And essentially what I did, use the calculations, the simple future value calculations and present value calculations. The one that drives people crazy the most is this alternative one, because you need a 10-year study period. You have a 7-year machine. So you can't make the machine go to 10 years. You have to buy a second machine. At the end of that 7-year period, you're going to buy a new machine for $50,000, just like the $50,000 you paid here. So, okay, my slides are off a little bit. But, so, add up the initial cost today, salvage value of that first machine. Then you have salvage value of the second machine, which they gave you here, discounted back to year one. And the present value of that second purchase. Similarly, second machine, $75,000. You're going to sell it at the end of 10 years, even though it can go for 13. You're only studying it for 10. Why? Because some twit on the board said 10 years. You get a present value of that, salvage value of that, and that gives you your $68.52. Anyone see any icky way of, so philosophically for this? I'll tell you why I hate it, since no one wants to speak up. Because it sort of devalues, essentially, when you say, hey, I'm gonna have to buy a new machine, only use it 3 years and then sell it, it disproportionately puts some cost factors that you don't necessarily get the inherent worth of the second machine. I mean, if this was a 9-year machine, you said, oh, we're gonna buy a new one to make that 10-year study. Was it really fair to say, I'm gonna buy a brand new machine and then sell it next year, just so I can give you a study period? It creates some inequities in the proportional worth of the relative options, in my opinion. But you do see this out there, so even though I dislike it intensely, I talk about it because it is out there, and I think it's a volatile one to use, but it's out there.
So are you equating? So are you kind of equating this to like when you buy a new car and you drive off the lot, that the depreciation is substantially more at the beginning and then lessens the older the car becomes?
Actually, that's actually not a bad analogy. Never thought of it that way, but yeah, it's kind of, it does say that you sort of, there's a diminished value, and there's also a lack of accumulated worth for buying the second machine on the alternative one. Because it's really, you're buying a machine that really could go 7 years, and you're saying you're going to sell it less than half its lifetime. Is that really an efficacious way to do business? This does come up quite frankly often in regulatory issues where certain machines like in healthcare have to be changed out by law in certain periods of time. And if they have a manufacturer who has a 7-year machine and you got to have that respirator for 10 years, you buy a new one. You know you're going to throw it away at the end of 10 years and it's redundant. But it does create a sort of old value. In one sense, I would say, I'm going to do something on this in front of you. I actually think it makes more sense to have that way. But no, bear with me, but I think it's a little easier to see when I do it like this. Because this is the first machine, this is the second machine. The value of second, we call it second. This might help some people sort of say, okay, now I get it. But first purchase, initial price, salvage value. Second person, initial price, salvage value to get that 664. Second machine here, first machine here, and everything discounted back to year one. But that's how they do it. They just assume you're going to buy another one and then stop using it so you can come up with a 10-year equivalent. Again, I'm not going to defend it because I don't like this, but it's out there. Be prepared for it. Now then, one last things I'm going to go over, ooh, goodness, getting late, is our second last thing, present infinite analysis period. And that's saying when you got to have you want to have how much money to invest now so I can have so much money coming back to me every month forever. And this is a book I actually talked about. It's how government works a lot, because they come up with, they're going to build a national park, and then they have to say, okay, how much does it cost to maintain that national park every year for perpetuity? So that means you got to put so much money in the bank now, and so we can maintain it on the interest forever. Well, here's the thing. Okay, how much must we set aside now? How much do we have to put in the bank today so we can pull out $45,000 or $5,000 a year forever? I'm not going to go through the derivation. The book's pretty simple on it, but essentially you have this P for principal we have to put in the bank today to get an annuity of $5,000 a year at 4% interest. Well, you divide the $5,000 a year you want, that A, divided by the 0.044 or 4%. That says in order to be able to draw, if you can guarantee you get 4% a year forever on interest rate, you put $125,000 in the bank, you can pull out $5,000 a year forever. That's what it's trying to do. You get all the pension plans work this way. Although they tend to have an incremental, I almost use the word gradient, don't let me use that word, but they have an incremental cost factor that goes on top of this. But it's a simple calculation, but this is for perpetuity. You just want to be able to pull out an amount forever. So, hey, it's a little different than the regular annuity calculation, because investment analysis will often say, okay, how long do you want to live after retirement? Well, if you want to have $100,000 a year to live off in retirement, you plan to live 30 years, how much do you need to have in the bank when you retire? That's how they make these pension calculations and that. But this comes up, so just put it in there. Now then, multiple alternatives. This is a tricky one. 5-8 on page 171. Getting close to the last thing to do. Now then, we're going late. I may have to figure out something else to do because I don't want to keep you here forever, because some people are going to fall asleep and disappear. All right, you got multiple alternatives. You got a pump that operates 2,000 hours a year. You got different pipe sizes and different alternatives and different operating rates and initial cost. Okay, so obviously you need the cheapest one. 3 alternatives, pipe sizes. Well, first you have to figure out, because there's an annuity involved, because you got a pump that operates per year. It gives you this nice example. Construct a 6-mile long tunnel into the mountains. 6 miles sounds really cool, but doesn't really impact it. During the 5-year construction period, the contractor will need water from a nearby stream. She wants to construct a pipe to get that water, and the cost of the pipes is shown. Again, initial cost of pipeline and pump, and the hourly cost of pumping at $2,000 a year, or 2,000 hours a year. So you got a time period, and you got amounts per year. So $2,000 a year times $1.2 is an annual cost of $2,400. You've got an annual cost that's the same. It should start thinking about a word, annual cost, annuity, same amount every year. The duration. Duration is 5 years. How do you know that? They told you. Now then, they also say the lowest rate which you get for money is 7%. So now they talk about this minimum active rate of return. You'll see that MARR, or minimum acceptable. They call it attractive. We always said acceptable. Basically, that's that corporate policy number that said we need a certain rate of return. So you get your 2,000, your annual costs for each one for this amounts. Step one. Then you basically have an annuity for each value. Size 1, we calculated the annual cost on the payment side of $2,400. Future value is 0. It's going to be used for 5 years. Our discount rate they gave us is 7%. So the present value of that $2,400 for 5 years for pumping is $9,840. Similarly for each one. You got outflow of $1,300, 5 years, 7%, 53. Cool. Each one of these alternatives, you do this present value calculation, given you have an annuity, i.e. payment, and here we go to the magic of Disney. Not going to be really zoomy, but let's do it. I'll do it this way, make it even smaller. So here's what I did. We got hourly cost. Now, so now then, cool. Then you got present value and initial costs. You calculated your hours per year down here, annual and your annual amount. 5 years at $24 a year, $9,800. So you have your initial cost. They told you in the nice little chart, initial cost of $2,200 plus the present value of the annual payments of $9,840 gives you a cost of $31,840. And you do that for each one of those, and then eventually you find out that the cheapest one to buy is this $28.33. So you do the math for each one. Each one has a different initial investment. Each one has a present value of annual costs. And if someone really wants to get crazy, 2,4, let's see, go over here so you can see it. Let's assume this year is 2,400, 2,400, 2,400, 2,400, 2,400. The net present value of 240, please make me right, Lord. At 7%. Oops. Made a mistake. 2,400. Now then, I'm going to do net present value. Oh, I did it in the same square I'm talking about. I'm going to show you a trick. Why you should love the net present value function. Another way to do this is say rate, 7%. The values are $2,400 a year for 5 years, which equals $9,840. Same as that. This annuity for every year is the same as just saying, hey, you could have done this in the chart and said this per year plus initial outflow of 22,000, and then is equal to, or I should say that minus that. Did it backwards. Didn't do it. But bottom line is you can use the exact same calculation. Instead of trying to find a payment value, you put it in the thing and say net present value of that at 7%. It gets you that same 98,470 or 98,440. Gets you the same place. Enough said. Because people are going to fall asleep soon. All right, multiple alternatives. Bottom line, least costly one, we add up the annual costs. You treat it as an annuity, 5 years, or you can just put it in a table and highlight for net present value. Either one works. There's multiple ways to get this done. Strip mining. Now then, last example, one more example after this. Gotta go to bonds. I'm gonna go through this quickly. If I'm going too fast, please stop me. So you got a strip mining purchase for $610,000. And it's gonna generate $200,000 in 10 years after you initially bought it for $610,000. At the end of the period, the government's going to make you put it back the way it was when you bought it for $1.5 million, more than the resale value of the land after it is restored. using 10% interest rate, determine whether you can do this project. Again, book does this nice rounding. Net present worth is minus 610 today plus $200 per year in years 1 to 10. Basically, it's an annuity for 10 years that you're getting in. At the end of it, you can have 1.5 million. So the present value of that future payment at 10%, which gets you here. So they give this nice thing about saying at rates below 4% and above 18%, net present value is negative. Basically, they're trying to get you to do what we're going to do in the future chapter, was say, hey, how often would you still do this project at different interest rates? That's another chapter. But here's what I did. Instead of doing all their nice individual calculations, I said initial purchase, 610,000. Put it in a table, because I can fit it in a table. Net present value gets really messed up when you start getting 400 lines of data, and you have to try and find the end of it and highlight it. Then reclamation, at the end of that period, 1.5 million. Well, the total you have is 610,000, 200 for 1 through 9, and 1.3 million for year 10, because you're going to pay an extra 1.5 million against the 200,000 you get that year. So is it worthwhile? Well, what I did instead of the digital version is a spreadsheet where I said, all I did is say, let's take the net present value of years 1 through 10. And you know what? Net present value doesn't care if you have a negative value in the middle of it. Like at the end here. Instead of doing their individual calculations like that, I put it in a table, said $610,000 up here, net present value of the cash flows, and net present value can deal with positive and negative values in between. That what makes it more fun to use. The fact that I suddenly go from positive, positive, positive to negative here, or if I had negative in the middle because I had to suddenly add extra maintenance costs, net present value can handle that. So getting net present value of 1 to 10 is 650,000, plus the $610,000 I had to pay for the mine in the first place is that 40,598, which is equal to what the book calls 41. I went through that really quickly because I'm keeping you guys here later than I want to. We good? Anyone good on this one? Oh. But treat it, if I sound like this is a sales pitch for net present value tonight, it's one of the best functions out there for a lot of things. The book takes you into bits and pieces, but you can make your life so much easier if you get these Excel functions handy. Okay, now the big one we're doing now for last is bond pricing. And this is because it's out there in the real world. This is a bond, a real bond. Bonds have certain things on them, like this. Has a face value. Face value, $1,000. How much it is? Interest paid, 6.85%. That's the interest rate. That's our I. We have our present value, interest rate, or it could be future value, depending on what it is. And that's part of what we're going to talk about. It also says maturity. Face value is repaid. When the bond at the end of its time period is due, in this case, it's due in 1978. If you bought this in 1977, a year later, they'll pay you $1,000 with interest before that. So due December 1st, 1978. So it has different rates, markets. So how do you value this? And this is, if you ever watch, in the news, you'll hear them talk bond market prices. They're one of the great ways people like to track them. Bonds right now are really dirt cheap. They're not a great investment for most people. They're only as solid as people sell them. There are U.S. savings bonds. There are in this case, power company bonds. Corporations can issue bonds. Theoretically, an individual can issue a bond if you can get someone to invest in you. Because when you're buying it, essentially it's a loan of money. And you know that at the end of the period, you're going to get paid an amount of money, a future value, December 1st, 1978, of $1,000 was being paid on this bond. So, and it's going to be paid at a 6.85 interest rate. So the question is, how much should you pay for a bond? And this is, again, you just watch, put on Nightly Business Report sometime, or pull up the Wall Street Journal, you'll see bond markets. At the back of the newspapers, on the financial section, they would have lists and lists of bond prices for different types of things, and bond ratings, meaning ratings of AAA bonds, meaning it's solid. People issuing it probably aren't going to go bankrupt. Years ago in the 80s, there were junk bonds being sold, meaning that they had a very low likelihood of being paid back, but they paid you such massive interest that maybe you buy it anyway. So bear with me on this, because we're going to use a lot of the same concepts we had on how to value it, but the terms of a bond affect where you stick stuff in for the right slots. 15-year municipal bond was issued 5 years ago. Trick question. How many years to maturity? Who can answer? How many years until maturity? I got all night.
10.
10. Yes, it was issued 5 years ago. So only 10 years to go. So any calculations you're going to do aren't going to be on a 15-year bond. You got 10 years left on that bond. What happened in the past, we don't care about. We got 10 years left till we can collect our $1,000, because that's what it says the face value is, paid semi-annually, twice a year. Very common on bonds. The coupon interest rate is 4%. On this value, it says 6.85 on the coupon rate. Face value is $1,000, like that example. But in this case, it's 4%. It's paid semi-annually. Cool. What is the bond price if the market rate is 6.09%? Now then, this is tricky. The amount you get paid is 4% semi-annually. So you got to remember, your old interest rate, this is just like compounding. 4% annual rate paid semi-annually means twice a year you get paid 4% or 2%. 2% of $1,000 is $20. And that's where they get their payments. We have 10 years to go, paid twice a year. That means 20 payments, semi-annual. Again, exactly like the compounding issue we had on loans. So, semi-annual interest rate, they say is 3%. Okay, 3% is the 6.09% divided in 2. So when I get down to it, it's 0.0045%. Or yeah, 3.045 is the actual interest rate, because you're splitting this in half, because it's semi-annual, twice a year. The rate 4% here, and that's where you got to make sure you don't get the coupon rate and the interest rate mixed up. The coupon rate is interest on the bond. The market rate is interest, whether it be inflation, market prices, whatever it is. That's the rate you're going to discount the amount. This 4% here is to determine the amount of payment that happens each year, which is 4% times $1,000 divided by 2, because it's paid semi-annually or twice a year, every 6 months. So that's where they get this present worth of 20 years, because it's twice a year for 10 years, 20 payments. 3% because it's twice a year, half of the discount rate, 6.09. Again, over 20 years for your interest factor. And at the end of 20 payments, you get the principal of $1,000 paid to you. Adding those two things together, you get $851.24 for that part. How I did it on mine? Last example tonight, guys, so bear with me. Oops. Oh, don't do this to me now. I dusted out my mouse. So now what I did is I did exactly. And so you'll see my answer differs from the one in the book. I did interest rate is 4%, but it's divided by 2. 4% times semi-annual is 20%. because it's 4% times 1,000 is $40. Semi-annually means you cut it in half because it's twice a year, $20. That's where the amount you get, the payment you get every year is $20 twice a year, 20 periods. At 3.05, which is really 3.045. The book cheats and just says, oh, close enough. 3% is half of 6.09. But I did mine exactly. It gives the present value of that. So let me bounce around to get my value. And that's where we get into the bond price, what you would pay. You have a future value of $1,000, meaning when it matures, you get $1,000. You have 20 payments of $20. Gives you present value. The amount you've been willing to pay for that bond today is $845 versus their, say, $851. The difference between $851 and my $845 is rounding. Mine's exact, theirs is estimated. Okay, now then, I'm gonna give you guys a choice. I think tonight, I may make the breakout sessions optional if someone sticks around and work on the problem, but I do need to go over the article assignment. How's everyone doing? It's been 2 hours. People need a break before I come back and talk about the article assignment. Anyone need a break?
I could use a few moment break.
All right, let's go. Don't want to shortchange you. 10 minutes? 10 minutes enough, or you want more? I got 3 people saying let's finish. People say I could use a break. Let's take a quick 10 minutes and I'll get you out of here by 5:30 unless there's lots of questions about the article. I'm going to skip the breakout sessions tonight. I may offer I'll post a office hours this week if someone wants to have a specific one to go over stuff. So let's take 10 minutes starting now. I'll see you at 5:22.
Awesome. Thank you.